Hello. In this very brief video, I'm going to go over section 11.5, and this is all about finding extrema. All right. Okay, so for this problem, we have a g of x, and it's a parabola, right? And we have a closed interval from -2 to 5, including -2 and 5. Okay, so we want to know where the absolute max and min are on this interval. And just looking at these graphs, just in general, you will have absolute max and absolute mins. That means the highest and the lowest part of the graph on this interval. This will either occur at one of the endpoints, or perhaps both, or somewhere on the interior, so somewhere in the middle. And that's what we're trying to find out in the second half of this question. Okay, so for the first one, we want to know the correct graph. And so let's see, we have a parabola, like I said. It's going to be positive. There's a +1 in here, so that means that it opens up rather than downwards like B and C. So now let's focus on A and D. So which one fits our function? So a quick way we can figure that out is just plugging in our endpoints, because that seems to be the difference between the two. So let's plug in -2 into our function. And I get +4, right? -2, so +2. Whereas if I plug in g of 5, if I plug in 5 wherever C and X, oops, -2, I get 25 minus 2, or 23. All right, so both of these are positive, but to the right endpoint is going to be higher than the left, so that's D. All right, so I imagine that this is 23, and then this is probably 2. So that's why D is our answer. So now we can look at the absolute min. So using our graph, we can kind of see that the absolute minimum happens here. Okay, and that occurs when x is equal to 0. So even if we didn't have the graph and we knew that it happened at 0, we can get an actual answer rather than an approximation. And so that's -2. So that's probably -2. So the value is -2, and this occurs at x equals 0. And then going back to our graph for absolute maximum, that's the highest value, or the largest value my function takes on within this interval, and that's up here. And we found that point to be from plugging in the right endpoint, so this is 523. And so again, the absolute maximum, this is our value of 23, and this occurs at x equals 5. Let's look at another example. We have h of x is the negative cube root of x. Okay, so, and this is our closed interval. Oh, +1. All right, so a little more difficult, but we know that a root function, a cube root, square root, kind of looks like this. All right, and then that negative in front means I need to flip it over the x-axis. And then this +1 all the way at the end means that I shift it up. So let's see which one shifted up by 1. So maybe something like this should have that kind of form, and we want to know what it's like on 27 to 64. So let's plug in those values real quick. So I'm not concerned about the entire domain of the cube root of x, the negative cube root of x +1. So if I plug in 27, I get the cube root of 27 is 3. You can use a calculator if that was not obvious. So I get -2. And then if I put in my right endpoint of 64, I get the negative cube root of 64 +1. And then the cube root of 64 is 4. So that gives me -4 +1, or -3. So then that means I should have the points 27, -2, and 64, -3. So if we look very carefully with our graph, it seems that A is probably our most likely one. See how C and D aren't really flipped over the x-axis, so that's if this negative wasn't here, but since we have it, it's flipped. So we can throw out C and D. And then if we look at B, these values are just off, I think, by 1 perhaps. This might be -4, whereas our A is -2 and -3, which we would want. Right, so using our graph, we can see that it seems it's a strictly decreasing function. So my absolute maximum occurs, and I know it's kind of hard to see, but my absolute maximum is here at my left endpoint, while my absolute minimum is my right endpoint. All right, so my right endpoint's my absolute minimum. So its smallest value is -3. And this occurs at 64. And then my largest value is -2, and this occurs at x equals 27. For this problem, we have something similar. We have a function over here in some intervals, and we eventually want to know max and mins. So we are able to find this without a graph. Unlike the last problem, we can use derivatives to find these max and mins values. So the first thing that is suggested, and anyway you should find, is our first derivative, which is kind of convenient here because our function is a straight line. It has an y-intercept of -1 and a slope of 8, so it's a line. So then that means that it has a constant derivative, right? If we did the derivative of this, it would just be the derivative of 8x, which is just 8, plus the derivative of -1, which is 0. So our derivative is just 8, and this just means that we have a constantly increasing function. So our absolute minimum and maximum, they're going to occur at the endpoints because we have a strictly increasing function. And so we're concerned about this stretch from, and it's just an approximation, but from 0 to 4, wherever 4 lands up. And notice how my right endpoint will be my max, and my left endpoint will be my min. So I'm going to find my endpoints. F of 0, I'm just going to plug in 0 into my original function. That gives me -1. And then f of 4, plug that in for x, and I get 32 minus 1, so 31. And so my function takes on values as small as -1 and as large as 31 on this interval. So my maximum is at 31, and that's at x equals 4. And then my minimum value is at -1, the smallest value, and this occurs at x equals 0. Right, and for B, it's kind of the same kind of game where it's the same function, and now we just have a different interval. So f of -3, let's find out what that is. 8 -3 minus 1, so I get -25. And then let's plug in our other endpoint of 2. So 8 times 2 minus 1 is positive 15. So again, my function takes on y values as small as -25 and as large as 15 on this range, on this interval. So that the absolute maximum value is 15, that positive 15, and this occurs at x equals 2. And then the absolute min is this -25, and this occurs at -3. All right, let's do one more. This one, it doesn't ask you to take the derivative explicitly, but we will use that. So f prime, it's actually the same as before. It's 8, right? The derivative of 8x. So again, we have this linear function where it's just strictly increasing. So again, the absolute mins and maxes will occur at the endpoints. So all we need to do is find the endpoints and decide which ones are the max and which one's the min. So f of 0, just plug in 0 into our original function, I get 7, and then f of 8, plug in 8, and I get 64 plus 7, which is 71. So my maximum value is a 71. This occurs at my right endpoint, and the smallest value is 70, and this occurs at my left endpoint, x equals 0. Same thing for part B, f of -3 is 8 times -3 plus 7, and that gives me -24 plus 7, so minus 17. And then f of 4, 8 times 4 plus 7 is equal to 39, right? 32 plus 7 is 39. So again, my absolute maximum value is 39 at x equals 4, and the smallest or minimum value is -17 at -3. Okay, so we now have some conditions here. We have 2 comma f of 2 if f prime of 2 is 0 and f double prime of 2 is greater than 0. So greater than 0 means positive. All right, so we know that we might have this, or we do have this point 2 comma f of 2. That's right here. And we know that the first derivative at this point is 0. So it has a horizontal tangent line. And then from this other piece, we know that the second derivative is positive, so that means that I'm concave up from my original function. And so what does this tell me in terms of maximum or minimum? That we have a minimum, right? 2 is a local minimum here. Let's look at another example. Let's say we have this, let's see. We have this 0.5 comma f of 5, and it's here. All right, what else do we know? We know that the derivative at 5 is this 1, so that means my tangent line at this point forms this kind of a line. So it means that it's increasing because it's positive, right? And we also know that my second derivative is negative, which means that we're concave down. So perhaps my graph would look something like this, maybe. And so this shows that we don't actually have any max or min here because we are increasing in concave down. So this will be neither. All right, so that sums up 11.5. It was kind of a quick section, but just highlighting the maxes and mins. So this will be important for optimization, which will be our last topic, our very last topic for the semester. So I will see you for that video very soon.